Hello students, in today's lab we will be talking about Richardson extrapolation. Before we start, I want all of you to remember our last video on numerical differentiation. There we learned about three different numerical difference formulas, the central difference one, the backward difference one, and the forward difference one, and used that to calculate the derivative of a function without using the function but by using few discrete points that we acquired by putting in the x value into the main function to get the y value. And all the basis of this difference formulas were the concept of gradient, which was the change in y-axis divided by the change in x-axis. So Richardson extrapolation is nothing but a derived and expanded version of the central difference formula. Here in the blue circle, we can see that we have the central difference formula. We can recall that this is the formula used for the central difference one, where the first parameter was the y value when we inputted x plus h into the function, and then deduct x minus h corresponding value of y, and then divide the whole thing with 2h. Okay, so this was fine till now. However, the problem with this is the accuracy and the error. The error, as we have already seen in the last lab, that the errors for this kind of difference formulas are pretty high. So now, to be exact, the errors are big O h square, at least for the central difference one. What we want is we want to decrease this order of error because of course better accuracy means lower error, and that's actually the thing that everyone wants. Okay, so to start the Richardson extrapolation, we will be using the Taylor's theorem. You can find this formula in Google or any other place. So if we expand these two functions using the Taylor theorem, we will find this extended function. It is nothing but substituting the corresponding values into the Taylor theorem's equation. We can see that as we move towards the right end of this equation, the power of h keeps on increasing by 1. So, for the sake of this equation, we have stopped at the h to the power 6 because h, as we have already learned in the last video, that h always lies between 0 to 1. So anything between 0 to 1 is basically a fraction. So if we increase the power of a fraction, that h to the power 7 or h to the power 8 or and so on, the power that the value will always be much lower than the normal value of h, or that of h square, or that of h cube. So we can pretty much say that the order of h cube, that is the value of h to the power 6, is approximately equal to the value of h to the power 6 added with the rest of the terms. Since the value keeps getting very small and thus becomes negligible in a way. Okay, that is why we have stopped at this point in the Taylor series and have not expanded after h to the power 7 or so on. Okay, so after expanding, we can see that in the central difference formula, the second term, the second equation, 5.3 equation, is deducted from the 5.2 equation. So after doing the deduction, we can see that we get these two terms are, and we are left with this thing. So by subtracting this from this, we get this, and these two terms are cancelled out as well, and subtracting this too, we get this thing, and these two terms are again cancelled out, and so on. And so since the order of h is cancelled out, we can assume that there are, of course, a second order of h, that is h to the power 7, and we place this in here. So after substituting this whole equation into this equation, we get this thing, that is we will be dividing this equation by 2h, which is done in here, and simplifying the equation gives us this thing. After reaching this equation, we can see that the central derivative, the formula of central derivative is equal to this formula using the Taylor theorem. Okay, so the thing that we need to keep in mind that f prime x, that this term is equal to the actual derivative of the function. We usually denote the derivative of a function using f prime x. So we are actually trying to find this value. But using the central difference formula, we can see that there are the other remaining terms that are affecting the accuracy and increasing our error of the calculated derivative. Okay, so what we can do is we can try to improve this equation. So how can we do that? So here the highest value of h to the power is 2. We have h square, and we know that the error is correspondingly correlated to the h to the power value. So since we have the highest power is h square, if we can deduct, or remove this term from the equation, we will have an error of lower value, because h to the power 4 is less than h square. Since h is a fractional value, this value is h square is obviously much larger than h to the power 4. So what we are focused on right now is how to remove this term so that we can improve the accuracy and that the error contains at max h to the power 4 value. To remove this term, we need to come up with another term containing the h square so that we can deduct that equation or that part of the equation containing the h square term and come up with something which does not contain this thing. This means that the equation that we want will not be having any thing containing h square, and the least possible value of h will be h to the power 4. So to do that, we can do that by using the value of h as h half of h. So if we substitute h divided by 2 into this equation, we can come up with this equation, and we have simply substituted this h as h divided by 2. Okay, so these two equations, we can use them to remove this term if we subtract this term, this h square term, from this term. However, we can see that there is a difference between these two terms, as this term has this thing whereas it does not have this thing. So to remove this thing, that is 4, because it's 2 square, what we will be doing is multiplying this equation with 4 so that we can get a term of h square that is identical to this term. Okay, so after multiplying this equation with 4, we can successfully remove this term from the equation, get a 4 in front of this, and of course in front of all the other parts. So this is done in here. We have multiplied this 5.7 equation with 4 and ended up with this equation. Okay, and later on, the main purpose of this Richardson extrapolation was to calculate the derivative, and so we need to subject this dh from this equation and come up with an equation which contains h to the power 4 as the lowest possible power of h. This means that the error for this equation is much lower, as h is a fractional value, and the higher the power of h, the lower the total value. Hence, the derivative will be more equal to the actual first derivative. Okay, so this is the assignment given for the Richardson Extrapolation lab, and this is very similar to the assignment given for the numerical differentiation lab, as we will be going through similar kind of tasks. Okay, so for the first part of the assignment are basically the codes, basically the equations that I have explained till now. So after those explanations, what we need to do is we need to import the particular libraries. The three of the libraries we have already learned in the numerical differentiation part. What else we have here is the pandas library, and it is important because at some point of the code, the skeleton code uses data frames. Okay, so after importing, what we need to do is we need to define the functions. Previously, we have defined the forward difference, central difference, and backward difference functions. And here we will be defining two functions, that is the dh function and the dh1 function. The dh function is nothing but the central difference one, because previously we had been using dh, or dh is previously defined using this formula, that is the formula of central difference, and we have learned before that central difference is the one giving the lowest possible error while choosing between forward, backward, and central. Okay, so we will be defining the central difference function here. We will be writing the same function that we have written in the numerical difference part. That is, just we will be deleting this line that is after the hashtag and returning this function. Basically, we just need to write this equation in here in this place, so that the function when called will return the value calculated in this equation. It's just one line. You just need to write this equation in here. Okay, so after we have defined the dh function, we need to define the dh1 function, and we will be doing the same task in here. We will be removing this line, that is, we will be deleting this line, and what we will do is we will return the Richardson extrapolation formula. So what is the Richardson extrapolation formula? It is to this thing, right? We now have this thing with us. So we will be placing this equation in this place. So what we will be returning is basically this formula. That is nothing but this formula. Okay, and as we can see that this formula already uses the dh function. And where can we get the dh function? We will be getting the dh function from here. So basically from this function, we will be calling up this function and giving a more accurate answer, or get the derivative using the Richardson extrapolation function. Okay, so this is what you need to do. I'm gonna remove this line from here. Okay, after that, what we have is we need to define the error function, and this is the second part of your assignment. And this is also again very similar to the error function that was defined in the numerical differentiation lab. So the error function in here is defined. So how do we calculate the error? We usually generate a derivative value using the central difference one, that is the dh function, and we generate a derivative value using the dh1 function. And to calculate the error, we need to deduct those values from the actual value of derivative that we are supposed to get, but we are not getting because we do not really have the function. We have used discrete points to calculate the main derivative. Okay, so what they are doing is, first they are trying to get the actual function that the real result is. They are trying to get that by calculating the actual derivative. So they have used the deriv function, which is a built-in function, and they have found the derivative equation using by calling this function on the polynomial f that were given to us. So after we call deriv on f, we get the main derivative function. That is the differentiation of the main polynomial. Okay, so after we get the function, what we need is we need to calculate the corresponding value of y for the specified value of x that we had previously passed through. Okay, so in y actual, we now have the actual answer of the derivative for the value of xi. Okay, so to calculate the error, we will be deducting the dh function, that is the central difference function of derivative value, from this y actual value. So we are supposed to write our codes in here. Basically, this is your assignment. This is the part of your assignment. So let's say that the error for central difference, that is the error for dh, is e1, and we can say that e1 is equal to y underscore actual y actual minus what? Minus the central difference function, that is dh. And what does this function take as parameters? This function takes one polynomial, the value of h, and some x value. And for this error calculation, of course, the values will be same as the value of h and x in here. So we will be passing on the function f, hs, and xi. Okay, x of I. Okay, so in this way, we can calculate the error while using the dh function. And in the same way, we can calculate the error for the dh1 function. And what is the dh1 function? dh1 function is the Richardson extrapolation 1 function, and of course we need to name it in a different way. Okay, so after calculating the error, what we are told to do is we need to append this into the difference error and difference to error list. So basically we need to append these values into these lists. And doing this is pretty easy. What we do is we write the name of the list where we want to add a value and call the function append. So we need to add the error E1 into the first, into this list, and we need to add the value of E2 in the second list. So basically, okay, no, we need to change the value. It will be difference to error. So basically, this is it. This is the code for the error. I have done it for you, but I have done it basically to explain you. You will not be given this, and you will have to write this on your own. So this is basically the end of your assignment. You are just supposed to write this to define these two functions and write the function of the error. After this, there are several code plots for you to run so that you can see what really happens. The plotting part is usually given in the skeleton code. So basically the graphs are plotted for different values of h. So we can see that when the value of h decreases, how the differential equation values vary. And we have plotted those in this function, and these basically used the linspace function, which is again explained before in the numerical differentiation value. The linspace function is used to generate the x values, and the corresponding y values are used by putting in the x, or by passing the x values into the dh functions. We get the derivatives, and we plot that by using the xplot function. But since these are part of the skeleton code, you won't be needing that for your to do your assignment. What basically you need to do is you need to understand what this function really means and implement this function into the code by writing the functions dh1 and completing the error function. Okay, so this is it for the Richardson extrapolation. Thank you.